And as you can see, it will present as a bijection between subgraphs and orientations.
Thank you. So I would like first to thank the organizer for inviting me to this workshop. I will present a bijection between subgraphs and orientations. And as you see from the subtitle, the Tutte polynomial will appear in this work. But maybe the first question that one might ask is, why is a bijection between subgraphs and orientation interesting? And what I want to show is that certain natural properties of subgraphs can be put in correspondence with some natural properties of orientations. So this is the goal of this talk. I will first present some definitions and known results about the Tutte polynomial, and then we will define a bijection. And first we'll define this bijection on spanning tree, because this is where it is easy to define. And to extend it to all spanning subgraph, we'll need to use some tools that appear as combinatorics of the Tutte polynomial. And here you will see something related to this Penrose identity. And then we'll see the properties of this bijection. So first, the definition of the Tutte polynomial. So we consider a connected graph, G. I will only consider connected graph for simplicity, but this is just for avoiding details. So now I want to define the Tutte polynomial of this graph, and for that I will look at subgraphs, more precisely spanning subgraphs. These are the subgraphs that contain all the vertices and a subset of the edges. So you have an example here in red, and I will look at two parameters: the number of edges that I will denote by cardinality, and the number of connected components. So here you have three connected components. This vertex is counting for one, the other. All right, so these are my notation, and with these notations, the Tutte polynomial is defined as a sum over all spanning subgraphs of these contributions. Okay, so this is definition, and maybe we can see a small example. So if we take the triangle, it has 8 spanning subgraphs. I sum up the contribution of each of them, and if I sum them all, I will find that the Tutte polynomial is x squared plus x plus y. All right.
And S is the number of edges in S.
Right. There is cardinality. Oh yes, I have to do also a small comment. So as I said, C of S is the number of connected components of the spanning subgraph. This is a spanning subgraph, or it is defined by the set of its edges. This is the number of edges, number of connected components. This is the number of vertices of the graph. This does not depend on the subgraph. And maybe so this Tutte polynomial is very important in graph invariant, because it contains a lot of enumerative information about the graph. And we can first see some of them in terms of subgraph. So maybe first I should make a remark on what is the exponent of y minus 1. This exponent, number of edges plus number of connected component minus number of edges, vertices, sorry, is the cyclomatic number of the subgraph. That is the number of edges to be deleted in order to break all the cycles of the subgraph. I can easily convince you of this property. Okay, so let's see some of the specialization of the Tutte polynomial. One specialization which is not very interesting is when you put all the two variables to 2. In this case, all spanning subgraph will have contribution 1, and you are just counting the subgraph, which are, this is just 2 to the number of edges. Now if you put one of the variable to 1, like let's put the first variable to 1, then you're selecting in this sum the subgraphs that are connected. So you are counting the connected subgraph of your graph. Dually, if you put the second variable to 1, then you are counting the subgraph that have cyclomatic number 0. That's the forest, the subgraphs without cycles. And if you put the two variables to 1, then you are counting the subgraphs that are both connected and forests, which are the spanning trees. All right, so these are easy specializations. They can be seen directly from the definition, but there are, in fact, a lot of other specializations. So here, I have put them in 3 categories: subgraphs, orientations, and others. And as you can guess, I will be mainly interested in the first 2 categories. So in terms of subgraphs, we have already seen some of them. In terms of orientations, the Tutte polynomial counts acyclic orientations, strongly connected orientation, root-connected orientations, score vectors, we'll see. And as I said, there are other specializations, but I will not talk about this today. So we have seen a very easy way of finding some of these specialization in terms of subgraphs, but how do we prove such specialization in terms of orientations? Well, the easiest way is to do an induction, because the Tutte polynomial satisfy a very nice inductive property. So you have these induction relations between the Tutte polynomial of a graph and the Tutte polynomial of the graph when you have deleted an edge or contracted an edge. And if you show that, let's say, acyclic orientation satisfy a linear recurrence of this type, then you automatically obtain that these orientations are counted as a specialization of the Tutte polynomial. But these proofs are not, inductive proofs are not very satisfying, because you don't see very well why this evaluation of the Tutte polynomial are really counting orientations. And also they do not explain the relations between subgraphs and orientation. Let me show you some of these correspondence. So I took my example of triangle. So here are the subgraphs, here are the orientations. So the evaluation 2 of the Tutte polynomial are counting is 2 to the number of edges. This is counting subgraph, and of course also the orientations. And now let's take this evaluation counting connected subgraphs. This is also the evaluation that is counting root-connected orientations. So what do I call root-connected orientations? So you have your graphs, you choose a vertex as your root vertex once and for all, and then you look at orientations such that every vertex can be reached from the root by a directed path. These are the root-connected orientation. These are not root-connected. Okay. Now the dual evaluation is counting forests. Here are the forests of my graph. And in terms of orientation, this evaluation is counting the score vectors. So what is a score vector? If you have an orientation, the score vector of this orientation is a function which associates to each vertex the out degree of this vertex. I've indicated the score vectors of each of the orientation here. And given the graph, you might wonder which are the function that correspond to the score vector of an orientation. And the number of such function is an evaluation of the Tutte polynomial, this evaluation. So for instance, here I have indicated a unique representant of all the score vectors of this graph. this score vector is represented also here. So I have chosen a unique representative of each score vector. So here I am also counting score vectors by this evaluation.
There is any canonical choice or
Of
a single representative in a class?
Yeah, there's some, but you have first to take a convention, and then you can. I will come to it later. You see that for instance, there is no intrinsic good represented. I mean, this is just it's just the same orientation, so I can choose one or the other at this point. Okay. Here I have given the two evaluation, and as you have seen, I have not cheated. I have put the same thing in corresponding each time. So if I look at the intersection of these two evaluation, this is in terms of subgraph, this is counting the spanning trees, and in terms of orientation, these are counting the root connected score vectors. So here maybe you wonder if this is well defined. Yeah, in fact, this is one thing that I should mention is that the reachability in an orientation do not depend on the orientation. It depends on the score vector itself. So this.
What's wrong with the very first triangle?
This is not a spanning tree.
Yeah, but below the blue one.
Sorry, this one.
I can get to everywhere from the root.
Yes, but I have taken a unique representant of my score vector. So this is already in there.
Ah. Thank you.
All right.
You say given the score vector. What was the last thing that you said? Given the score vector,
Okay.
there's a unique way of telling.
Okay, so you can tell from the score vector if one vertex can reach another. You don't have to look at the precise orientation. The reachability do not depend on the precise orientation.
Is it similar to the bunny test you have mentioned at the Abelian senpai, or is something different?
Sorry?
It is similar to the techniques in Abelian senpai, or nothing to do with that?
I don't know what you're talking about.
I thought because you mentioned that before, but in case, no.
You
Okay.
mentioned the Abelian sand pile.
Oh. No, this is not related to that. There is a connection, but it's more complicated. No. There is an easy criterion here to see if two vertices are reachable. Okay, so here now we will want to construct a bijection that makes some correspondence between properties of subgraphs and orientations. And first I will define it on spanning trees. And for that I will take a convention under the form of combinatorial embedding of my graph. So what is a combinatorial embedding of a graph? This is a choice of a cyclic order of the alpha edge around each vertex. So I choose arbitrarily a cyclic order around each vertex, and I call that a combinatorial embedding. And moreover, I want to choose a root, which is just a half edge that I distinguished.
And so then you get a linear ordering.
I get a linear ordering around this vertex. Yeah. Okay, so why do I call that an embedding? Because in fact this is also equivalent to the usual notion of topological embedding. So there is a one-to-one correspondence between this combinatorial embedding and the topological embedding in orientable surface when I consider this embedding up to homomorphism. So what is that correspondence? In fact, if you draw your graph on a certain surface, this defines the counterclockwise order around each vertex. So this defines a combinatorial embedding, but this is in fact one-to-one. If you take a combinatorial embedding, there is a unique surface and a unique way of putting your graph in this surface in such a way that this cyclic order is. So okay, so I'm only working here, but in order to give you some intuition, I will draw my graphs. That's all you have to know. And my root, I will indicate it by a little arrow pointing before the choose half edge. Okay, so now we are ready to define the bijection on spanning trees. And when I have my graph, embedded graph, and a spanning tree, I can make the tour of the spanning tree. I start from the root, and I follow the edges of the tree until I return to the root. This is the tour of the spanning tree. Now I associate an orientation to my spanning tree by saying that I will orient internal edges, that is edges in the tree, from father to son. So my tree is oriented from the root to the leaves. And the external edges, the edges not in the tree, are oriented in such a way that the ingoing half edge is encountered before the outgoing half edge. So for instance, if I take these external edges, around the tree I first encounter this ingoing half edge before the outgoing half edge. So this is the definition. And one nice thing, at least about this definition, is that this mapping is injective. That is, if I am given the orientation, I am able to reconstruct the tree. So how can I do that? Well, in fact, it is quite easy, because you see I have stated that for external edges, I encounter first the ingoing half edge. And this is the contrary for internal edges. I encounter first the outgoing half edge. So I will be able to start making the tour of the tree, and each time I encounter an edge, decide whether it is internal or external. So let's start. I start from here, and I want to decide on this edge. I see that this is an outgoing half edge, so this has to be internal. This has to be an edge in the tree. So I know how to continue the tour of my tree. Then I encounter this edge, and then I know that this is, I see that it is ingoing half edge, so this has to be an external edge. And I decide like that. So I continue my tour, I encounter this edge, I see that this has to be internal, and like that I'm able to decide on each edges and recover the spanning tree. So this is indeed injective. And now we'll see how to extend this into a bijection between subgraphs and orientation, and this is where the polynomial will enter into play.
And it will follow from this that all the orientations you have here are root connected,
right?
And they all have,
they are root connected, and they also
have all different score vectors.
Yes, exactly. They have all different score vectors.
And every score vector of a root connected orientation is
exactly. So this, in the case of planar graph, this will be my minimal orientations. And in the more general case of the genus, you still continue to have a unique representative of each score vector. But I will come to it later. Okay, so what I want to do now is to associate a spanning tree to each subgraphs in order to continue to extend my definition. And this is where this that polynomial will appear. So let's consider spanning tree. I will now tell you what are fundamental cycles and cocycles. So if I have an external edge, this one, the endpoints of this edge are joined by a path of the tree. So adding this edge to the tree creates a cycle, which I call the fundamental cycle of my edge. Now the dual construction. If I have an internal edge here, if I remove this vertex, I am cutting my tree into two subtrees. And I will call the fundamental cycle is the set of edges that is joining one of the subtree to the other. These edges. All right. Okay, now I will call activities. These are not the same activities as you are using.
Sorry, can we just back up? Was that necessarily closed, that construction?
Sorry?
It's a co-cycle, so it's closed? I mean, it's a loop, it's a union of loops?
No, it's the dual thing.
It's the dual thing. It's a set of edges that disconnect the graph into exactly two parts.
Right, okay.
Well, it's a set of edges that disconnect the graph and which is minimal for this property and inclusion. Okay. Okay, let's now define activities. So we have a spanning tree. We now know that we can make it store, and this it defines an order on the edges.
By the way, is this tour the depth first search?
No.
No.
No, because here I'm taking really any spanning tree. I'm taking a spanning tree and making it store.
Oh, I see.
Wait, does that depend on the combinatorial ordering?
Yes.
Embedding.
No, I'm sorry, but the ordering.
Okay. So what you are aiming at is these properties of what are the internal trees and in fact you are too much in advance for what we are doing now because.
No, maybe I was asking something else just about the tour.
Mm-hmm.
Given the spanning tree, is it true that this tour is the depth first search of the tree?
It does not really make sense. It's just the tour. I mean.
First searches of a graph, not of a tree.
No, but you can consider the tree.
Yeah. Okay. You can always say that, but.
Well, but the tree there is.
Okay. Alan. Let me answer this question. So the problem, you are indeed doing the depth first search on your tree, but I don't want only to order the edge of my tree. I want to give a linear order to all the edges of the graph, and this is why I'm doing the tour really on the embedding. I mean, I want to go through all the edges. This is the order. So it's not just an order on the edges of the tree. Okay. Okay, and now I will call an edge active if it is the first of its fundamental cycle or cocycle around the tree. Okay, so for instance, 4, its cocycle is 4 and 6, and 4 is the minimal in its cocycle. So this edge is active. 5 is alone in its fundamental cycle, therefore it is active. 1 is the first in its fundamental cycle, which is 1, 2, 3, therefore it is active, and the other edges are not active. And I denote by I of t the number of internal active edges, E of t the number of external active edges. Okay, and the theorem is that the Tutte polynomial is given as this sum over spanning trees of x to the number of internal active edges, y to the number of external active edges.
This is what is called partitionability or shellability, or is something
What's
else?
related to?
That's related to, and we are going to come to it. But
Related to the partitionability that was used in the Penrose lemma, but it's not.
okay, it is not the same because I'm not using the same kind of activities. But yeah, this is really a kind of Penrose activity, but more general because I'm not the Penrose the Penrose identity is just when you put 0 and 1, and here I'm considering the full Tutte polynomial.
Right, so Penrose would be only external or only internal.
Only external activity on internal. No, only external activity, but on a special class of tree. Okay, but let's just make a simple example to be sure that we understand what we are doing. So if we look at the triangle, we can take the three spanning trees, look at what are the active edges, and this gives this contribution, and we recover the Tutte polynomial of the triangle. Okay, so I'm not the first to write this identity. I should mention that this identity is a bit surprising because you see that these things depends on my embeddings. They are defined after I've taken this convention of an embedding. But when I sum over all trees, I find something that is completely independent of the embedding and that only depends on the graph. And this is the Tutte polynomial. Okay, so this identity is not trivial. So I should mention that there are several other characterizations in terms of activity, several other theorems that look like that, and the first of them was written by Tutte in 54. So this is, I guess, before Penrose, and it was based on a different kind of activities based on a linear ordering. This is a different one. It's not comparable, but
yours is not just a special case?
No, in fact, it is not a special case because here I am. So true, when I have a tree, I'm defining a linear order, but this linear order depends on the tree. Whereas in the case of the Tutte activities, you take a linear order once and for all, and this is your convention. Instead, I'm taking a combinatorial embedding as a convention. So this is not a special case of Tutte's theorem.
Changing the ordering with the tree.
Depends on the tree. Depends on the tree.
Okay, so these activities of Tutte on this one are in fact can be seen as a special case. So this paper by Gordon and McMahon give a more general context in which you can obtain such a theorem. So
does it include yours as well as?
This includes mine. If you can, in fact, when you want to prove that, more or less you are proving that you fit in this context. So well, in fact, when you want to prove such a thing, the easiest way is to do by induction. And when you do by induction, in fact, you are falling in this context. So the proof is not really using that, but I am indeed in this more general context of Gordon and McMahon. Okay, now, in fact, there are some other authors have considered some activities, but usually they consider external activities because they are easier to define. So there are different work here working on these external activities, and Penrose as well is working with only external activities and not the full activities. And I should also mention along this line that there is a work by Las Vernias that gives a kind of activities to the orientation and give a characterization of the Tutte polynomial in terms of these activities of orientations. Okay, so there are other people that have been able to write such identities, and what is really the link with the previous definition of the Tutte polynomial? So the previous definition in terms of spanning tree, of spanning subgraphs. So what is the link with between these two? And this link is based on the partition of the set of subgraphs into intervals, as Alan was mentioning. So what is this? What is the construction behind it? So to a tree, I will associate a set of subgraphs. These are all the subgraphs that can be obtained from T by either adding external active edges or removing internal active edges. So all the active edges, you can put or not put them into the subgraphs. So this forms an interval in the lattice of subgraphs. Here you have removed every edges that you could, and here you have put them. You have put all the active edges, and the subgraphs that you associate to T are all the subgraphs in between. What I want to say is that this sum over subgraphs can be written as a sum over trees of a sum over subgraphs. So the first thing is that the set of subgraphs, the set of intervals form a partition of the set of subgraphs. So the set of subgraphs is a disjunction of these intervals. Okay, this was done first by Crapo, I think, for the activities of Tutte, and there is a generalization by Gordon and McMahon. And so here is an example. Here are the 5 spanning tree of this graph, and I associate an interval to each of them, and I obtain all the subgraphs. And the second property is that if you look at these parameters, C of S minus 1, this is for a subgraph in the interval associated to T. The number of connected component minus 1 is the number of edges that you have removed from your tree. And the cyclomatic number is the number of edges that you have put, that you have added to your tree. So for instance, if you look at the interval, you have your tree. The connected subgraphs in this interval are the one between T and T plus. The forests are between T and T minus. And with these two properties, we obtain the second proposition saying that if you sum the contribution of all subgraphs in the tree interval, you obtain the contribution of the tree in terms of activities. This is these two propositions make the link between the two definitions. Here you obtain x as 1 plus x minus 1. Okay. And also you can see some of this. You can see that the Tutte polynomial is counting some natural class of subgraphs in this way. So here you know what connected and forest mean, but external. So a tree is external if all the active edges are external, and a subgraph is external if it is in an external tree. And internal is the same thing. So a tree is internal if all the active edges are internal, and subgraphs internal. Okay. So this gives the evaluation. These are the different evaluation of the Tutte polynomial counting the different classes of subgraphs. Here, external is a special case of connected, and internal is a special case of forest. And the Penrose identity, I think, is here. So if you put 1 and 0, you find the Penrose identity here.
Make an observation which
Yes.
might be a bit out of topic, but is it true that by this method one can maybe calculate the post-partition function on random graphs with a direct combinatorial method of tree, blossom, and then connected them, because the counting of internal and external vertices is done on the tree?
I'm not sure to say what you mean, but I don't have.
The model partition function on random graphs, not with the random matrix method, but with the blossom method of trees with arrows and so on.
Okay, maybe we can discuss that after the talk. I will now extend the definition and see the correspondence of properties.
This connected internal, this TG10, that's
Yes.
exactly the Penrose trees. Which
Yeah, these
occur
are
in
the
outdoor
internal trees.
parks.
So if you take not this kind of activities, but the BFS activities, you find the Penrose trees, but you have other kind of activities like TFS activities, or you just need external activities, and this is quite easy because there is a connection with SunPy model, and you can easily construct external activities which are natural by a method that we can discuss later. Okay, this is
more general partitionability schemes than this one.
Yes.
sorry.
You can find something different from the Penrose trees to have this.
Yeah, sure, you can.
No, the question is these are all partitionabilities. All partitionability schemes can be written this way.
No, he has particular ones, but the point is, any external partitionability scheme will give a partition of the connected spanning subgraphs. That's what I was
Right.
talking about. And dually, right, internal. Then you have a partition.
Once you have this partition, you see that all the weights cancel in the version 3 of Maya of this Maya expansion, and you only obtain these internal trees. So internal has a meaning if you have defined some kind of activities, but you are not bound to use the BFS one. You can use other types of activities. Okay, I have a subgraph here, and I want to say what is the orientation associated to it, and I will for that look at the tree in which the S belong. So this is the tree. These are the active edges in dashed, and I note how to associate an orientation to this tree. So now the orientation associated to S will be obtained from this one by reversing some of the cycles and cocycle. In fact, I will reverse the cycles and cocycles of all the edges in the symmetric difference. Okay, the symmetric difference is this edge and the loop. So I'm reversing the cocycle, the fundamental cycle of this edge and the fundamental cycle of this edge, and I obtain the orientation associated to my subgraph. And this defines a bijection between subgraphs and orientations. So if I take this example again, here are my subgraphs sorted according to their trees, and if I apply this works. This indeed make a bijection. All right. So now we want to study some of the properties of this bijection. And as Alan noticed,
No, I didn't notice. I just guessed given your result.
okay, so as Alan guessed, if you are taking a spanning tree, the associated orientation is root connected. This is just because the tree is oriented from the root to the leaves. So this is clearly root connected. And in fact, there is the dual property. So at least in the planar case, the dual property is that this orientation is minimal, meaning that this is my root, and I cannot find an oriented cycle in this of this type. All the oriented cycle will be oriented this way. Okay, this is a notion of minimality that can be interesting. This is minimal because this is the minimal element for a lattice of all the orientation of these having the same score vector. But so what remains in the higher genus is that these orientation are alone in their class of score vectors. So they are representative of the score vector themselves. And the second remark I want to make is that the fundamental cycle of cocycle of an edge is directed if and only if the edge is active. So here I should make counterexamples to convince you what is up, to show you what is happening.
Can you do it in white, please?
Sorry?
Can you do it in white? We
Yeah,
start to see.
sure. Okay, if I take an external edges that is okay,
Ah,
is that okay?
yeah.
Okay, if I take if I take an edge that is active, it is this way. You see that this edge is active. It is the first to be encountered. It is fundamental side cycle. Then you have something directed. But if instead I take an edge that is not, which is not active, you see that this edge is not active because if I make the tour of the tree, I will encounter this edge first. Then my fundamental cycle is not directed. Okay, similar. There is similar properties for the co-cycles. Okay, if I look at this edge, this is active, and the co-cycle will be directed because I will encounter all these alpha edges first. But on the other hand, if it is not active, I will encounter some external edges first, and this will not be a directed co-cycle. Okay, so these are just from some remarks to explain, to give you some intuition why this bijection has good properties, but these are the results now. So here I've represented on one side the subgraphs, on the other side the orientations. So I've sorted the subgraphs according to their properties. So general, connected, external. This is going from general to particular, and here from general to particular. And for instance, so in this column you have the external edges, external subgraphs which are not connected, which are external subgraph. Here the connected which are not external, and here the one that are not connected. All right. I hope you can read this array. And here I've put the corresponding orientations, and you see that I can put some natural properties. So here you obtain root connected orientation, and here strongly connected orientation. And here for forest I will obtain minimal, and for internal I will obtain acyclic. So the root connected acyclic activities are this evaluation of the Tutte polynomial, and they are the ones that are interested in this Penrose identity.
So didn't you say that minimal is for planar graphs?
Yeah, so you can of course give
So for a given
you can give a general definition of minimal. This has not a very interesting meaning when it is not planar, but you can still call them minimal. And the nice thing is that these minimal orientations are unique representatives of score vectors. If you take all the minimal orientation, they are you will have one. You will have the score vectors once. Okay, you understand what I mean?
So from the orientation, you can read off, for example, whether the corresponding subgraph is connected and whether or not it's a forest.
Of course, you look at
Right, but can you, if it's not connected, can you read off how many connected components it has? And
Yeah,
if
you
not
can.
A forest, can you read off what its cyclomatic
Yeah,
number
you
is?
can look at the vertices that are reachable from the root. This make your first tree. You have a forest on the other side. So this make the first part of your forest, and then you do the same thing. You cross an edge, and you do the same thing, and you recover like that the number of trees in your forest, for instance, or the number of connected components of your graph.
So that means that you can define a polynomial over orientation.
You can, but
with certain
this
numbers that will be equal to the Tutte polynomial.
you can, but then you have to be careful about the fact that the way that you are propagating to find these reachable parts depends on the embedding. So this is not an intrinsic property of the orientation. You need a convention, because the way you are exploring your graph, you take a convention on you have to take a convention on the way you are exploring your graph.
Convention how to choose the new route in particular.
Yes, exactly. So when you have finished with your part, you have to choose a new route, and this you will use the embedding to choose that. Okay, so mainly these are the results, and if I write them, this says that the connected subgraphs are in bijection with root-connected orientations, and as a byproduct there is an enumeration, which was already formed by J.N. Forests are in bijection with minimal orientation, which are in correspondence with score vectors, and this was the enumerative part was already formed by Stanley. If you take the intersection of the two first results, you find a bijection between trees and minimal root-connected orientation or root-connected score vector. If you take internal subgraph, you will find acyclic orientation, and there was already a bijective proof by Sagan and Gesser. This was first formed by Winder but rediscovered by Stanley, the enumerative result. If you take external subgraphs, you will have an bijection between external subgraphs and strongly connected orientations, and taking the composition with the previous previous characterization, you obtain two more bijections, so internal trees with root-connected acyclic orientation, external trees with minimal strongly connected orientations. That's it.
There's another question.
What about the SunPy recurrent relation?
Okay, so here you have here bijection between spanning trees and root-connected score vectors. This is so you have your. This is the first part, so you don't have to use this Tutte polynomial thing. So you have this. Okay, you have your tree. You know how to orient every edges, and you take the out degree. Okay, so this will be 2, 0, 2, 2, 1, 0, etc. Now, if you want to make a bijection not with root-connected score vectors, but with the SunPy configuration, what you will add is you will add something to this function. You will add the number of external active edges pointing to the vertex. So here +1, and that's all. You don't change anything else. So here it's still 1. This is still 1. Sorry, 2, and this make a bijection between spanning trees and SunPy configuration, which transfer the external activities to the level of the configuration.
Is it the same as the Corey-Levant bijection?
This is not the same because I'm not using the same kind of activities. So when I am saying that I'm transporting the number of external activities to the level,
And what about the second?
It's not the same activity I'm talking about.
Can you transport it?
But still, you obtain the result. I mean that the generating function of recurrent configuration counted according to level is a specialization of the Tutte polynomial.
What about the second variable?
No, but the second variable is a false problem because you.
What about bijection?
I mean, you cannot hope to have an intrinsic. You cannot hope to have an intrinsic definition involving both.
It's impossible.
No, it's impossible because if you take the triangle, you see that two configurations that have. I mean, you look at the different configuration. And you look at the different coefficients of the Tutte polynomial, you see that you need a convention because there are two configurations which are the same up to an isomorphism of your graph, and that should give different weight. And this is not possible. Wait, so this is not possible. This is not. There will not be any intrinsic definition that involves the two parameters. You can make a convention and then you will have the second parameters, but this is a bit artificial.
Can I ask a general question about partitionability? So let's say you have a map T to T plus.
Yes.
For however it's done, by Tutte's method or your method or Penrose's method, there are lots of them, right? Which partitions the connected spanning subgraphs into Boolean intervals based on trees.
Okay.
And let's say now you have another mapping T to T minus that partitions the spanning forests into Boolean intervals whose tops are trees. Okay. Is it true that those T minus and T plus automatically go together to make a partitioning of the whole Boolean lattice into Boolean intervals with centered at trees? Or do you need extra compatibility conditions between the two maps?
I would
and
say
if
that
so, what are the compatibility conditions?
I think that you need compatibility conditions. In fact, you might not start with T to T plus, but F to F plus. So to each forest, associate an augmentation, possible augmentation. This will give you a forest expansion that was used by Gesell and other authors.
And it will automatically have, at most, it'll have exactly one tree
I think
inside
that
it.
there you will be able to say something about the compatibility conditions. But if you just look at trees, I don't know. We should
Okay, so
speak
let's
about
propose
that,
this to everybody as a general topic to understand all these different partitionabilities and how they fit together.
Okay. Thank you very much again.